everyone. We want to introduce the concept of a surface integral. Now we know from before how to find the surface area. What we did was we take a piece of the surface, we project it onto the xy plane, and we found the surface area parameter. So any surface that's defined in the form of z equals f of xy, we said that the area was the double integral over the surface of ds. And then we came up with a formula that said that based on the projection, the region in the xy plane, fx squared, fy squared plus 1 dA. So this was a formula we developed earlier and we used often. So what a surface integral is now imagine rather than just finding the surface area, I have a surface where at every point on the surface I might have a different density, for example, and I want to find the overall mass on the surface, not just the area. So the form of a surface integral will be the double integral over the surface of some function of x, y, z integrated over the surface. Now, we have a couple of problems here. One is obviously we need to change this into this form, but also I have a function of 3 variables in a double integral. So going back to my definition of the surface, where the surface is defined as z equals, then this will become the double integral over the region in the xy plane, as before, g of x, y, f of xy. And now I replace ds with, again, the surface area parameter. Okay, so let's look at this first. Now let's consider an example where I define my function g to be the following, and my surface is going to be the top half of the sphere. So the first thing I need to do is actually find the surface area parameter. So we need to define a function, z equals f of x, y. So if we solve for z being the top half, this will be the square root of a squared minus x squared minus y squared. Now we'll find the partial derivatives, fx, which we've done before. We know that will look like this. Fy, and then finally the surface area parameter, which is the sum of the squares plus 1 under the square root, and that will end up being just a over the square root of a squared minus x squared minus y squared. Okay? So continuing, that would give us ds is a over the square root dA. So my integral in this case would become, okay, 2x plus 3y times a over that square root. Now looking at that integrand, clearly we would want to go with polar coordinates in this case. Now looking at this, in the xy plane that would be a circle of radius a, because it would be x squared plus y squared equals a squared. So moving on to polar coordinates, this would give us 0 to 2 pi, 0 to a times r cos theta, 2 r cos theta, plus 3 r sine theta, over a squared minus r squared under the root, r dr d theta. Now we'll evaluate this on another day, but the idea here is that I went from this question to this, and then we proceed from here.